Welcome back to the deep dive. Today we are tackling a subject that I think genuinely haunts the dreams of a lot of engineering students.
And probably quite a few professionals, too.
Oh, absolutely. We're talking about the absolute nightmare of simulating moving parts in computational fluid dynamics. And I don't mean just a simple spinning fan that stays in one place. I mean the chaotic, messy, unpredictable stuff.
The stuff that breaks all the rules.
Yeah.
The scenarios where the geometry changes so drastically that the math literally runs out of room to operate.
Right. And I want to set the scene for everyone listening. I want you to visualize a mesh, that grid of tiny little cells, millions and millions of them, that covers everything in a simulation so the computer can solve the equations of fluid flow.
Mm-hmm.
Now, imagine you have a scenario like two race cars overtaking a third one at, say, 200 miles an hour. Or, even better, imagine a lifeboat being dropped from an oil rig, plunging 40 meters down into rough, crashing water.
That lifeboat example is actually one of the benchmark cases for the technology we're discussing today. It's essentially the final boss of motion simulation.
The final boss. I like that.
Because you have gravity, aerodynamics, hydrodynamics, free surface waves, and a rigid body moving through all of it.
All at the same time.
Simultaneously, yeah.
Exactly. But think about the grid. In traditional CFD, the grid is, it's a continuous web. If those cars move 100 meters down the track, what happens to the mesh connecting them to the road?
Well, it stretches.
If it's a single continuous grid, you're stretching those poor little cells like chewing gum.
And just like chewing gum, eventually it snaps. In CFD terms, your cell quality hits zero, or you get what's called negative volume, it's exactly what it sounds like, a mathematical impossibility.
And the solver crashes?
The solver crashes, you get no results, and you have a very, very bad day.
So the old school solution was to brute force it. You'd stop the simulation every split second, delete the mesh, build a brand new one that fits the new position, map the data over, and then restart.
That's called remeshing. And while it works, technically it works, it's incredibly computationally expensive.
It takes forever.
It takes forever. And frankly, every time you map data from one grid to another, you lose a little bit of accuracy. It's diffusive, which means the sharp details just get blurred out.
So that is the problem, the engineering nightmare. But today, we're diving into the solution. It's a technique that feels a bit like cheating when you first see it, but it turns out to be some of the most elegant math in the field. We're talking about overset meshes.
Right. In the broader academic CFD world, you might also hear this called Chimera grids.
Chimera, like the mythological monster.
Exactly. The beast with a lion's head, a goat's body, and a serpent's tail. It's a hybrid, and that's precisely what we're building here, a hybrid grid made of different distinct parts.
And in the source material we're looking at today, specifically regarding SimCenter STAR-CCM+, it's referred to as overset meshes.
That's the term they use, yeah.
And the core concept is just core. Instead of one giant stretching grid, you have multiple grids that just sort of float on top of each other.
They overlap. They move independently.
And somehow the data just jumps between them across the void.
It's the somehow that we're going to unpack today, because it isn't magic, of course. It's very, very clever mathematics involving things called donors, acceptors, and virtual holes.
So here's our mission statement for this deep dive. We are going to explain overset meshes as if we're talking to a student who just watched their mesh explode.
We've all been there.
We've all been there. We're going to break down how the data makes that jump. We'll look at the specific roles of the cells, the hole cutting process, which sounds violent but is actually quite elegant, and why this is the go-to method when things need to move a lot.
And we should definitely cover why you wouldn't just use the other methods, like morphing. That's a really common point of confusion for beginners.
Absolutely. So let's start with the basics. Section 1, the core concept. What exactly are we looking at when we see an overset mesh set up on the screen?
To visualize this, imagine you have a background. Let's say it's a virtual wind tunnel. You mesh that entire volume with a nice, static, high-quality grid.
Okay.
That is your background region. It encloses the entire solution domain.
So that's my base layer. It's just air, basically.
Right. Now you have an object, a car, a boat, a drone propeller. Instead of forcing that object to be stitched directly into the background grid, you cut out a smaller box around that object. You mesh that small box separately, with a lot of detail right near the object. That small separate mesh is the overset region.
So I've got a big grid, my wind tunnel, and then a little patch grid with the car inside it.
Exactly. And you literally place the little grid on top of the big grid. They overlap, The car grid moves, translates, rotates, whatever it needs to do, and the background grid just stays put.
It sounds so simple, but it breaks the fundamental rule of old school CFD, which is that everything has to be connected, node to node.
It absolutely does. And that's why, before Overset became robust, we had to rely on other methods like morphing. And it's really important to understand the difference, because beginners often mix them up. The source material makes a clear distinction here.
Yeah, I saw that. The sources ask the question, why not just stretch the mesh? And that's morphing, right?
Correct. Morphing is where the mesh deforms. Imagine drawing a grid on a balloon and then you squeeze the balloon. The lines curve, the cells stretch, but the topology, the connections between the corners, stays exactly the same. No bonds are broken.
And the source says this is most appropriate for moving boundaries where the shape is maintained.
And crucially, for small deformations. That's the key. If you just need a wing to flutter slightly in the wind, or a pipe to expand a tiny bit due to thermal pressure, morphing is fantastic. It's fast, it's efficient.
But if you try to drive a car 100 meters down the road using morphing...
The cells behind the car would have to stretch 100 meters. You'd get these long, thin slivers.
Right.
And the math, the numerics, just despises slivers. When cells get that disported, the calculation of gradients, so how pressure changes from one point to another, it becomes wildly inaccurate. The simulation diverges and it fails.
That's where the source pivots to overset. It says overset is for large-scale motions.
Right. Complex body motions. Bodies that are close together, intersecting paths, or things moving very long distances. The example they give is two cars overtaking a third. You just can't morph that. You need the freedom to completely disconnect the object from the background.
There was also a mention of adaptive mesh refinement, or AMR. How does that fit in? Is that a motion strategy?
Not primarily, no. AMR is a mesh refinement method. It's physics-driven. So if you have a supersonic shock wave, AMR will detect that big pressure jump and automatically move cells smaller right there to capture the detail.
Okay, so it makes the mesh better where the action is.
Exactly. You can use AMR to help with motion, and we'll definitely talk about that later in the context of Overset. But AMR on its own doesn't solve the problem of moving a solid body across a domain. It refines the mesh, but it doesn't move the mesh.
Got it. Okay, so Overset is the champion for big movements, but now we have to get into the nitty-gritty, the mechanics. Because if I have two disconnected grids, how does the air in the background grid know that the car in the Overset grid is even there, let alone pushing it?
This brings us to Section 2, the mechanics of data exchange. This is where we meet the cast of characters.
I love this part.
In an Overset simulation, every single cell is assigned a specific status or role. It works almost like a hierarchy or a government office.
We have active cells, inactive cells, and the diplomatic corps, the acceptor cells.
That's a very good way to put it. Let's start with the active cells. These are the regular workers. They're the ones doing the math. In these cells, the discretized governing equations, Navier-Stokes, energy, turbulence, are being solved just like in any normal simulation.
So if I'm an active cell, I'm calculating pressure, velocity, temperature. I'm busy.
Yes. But then we have the inactive cells. This is the whole. Remember, the background mesh covers the entire domain, but there's a car sitting in the middle of it. The background cells that are physically located inside the car or are effectively replaced by the car's much finer mesh are marked as inactive.
So they're just turned off.
Completely. No equations are solved there. The source explicitly says physical values from inactive cells are meaningless. They're just ghosts. They exist in the computer's memory, but they are void of physics. They're just waiting to be reactivated if the car moves away.
Okay, so we have workers and we have ghosts, but the real magic happens at the edge, right?
At the perimeter. That's where we find the acceptor cells. These are the cells that separate the active cells from the inactive cells. They form the border of the Overset interface. They're the border grids.
And this is where the handshake happens. I want to break this down for the listener because the source uses some really specific terminology, donors and acceptors. It sounds a bit like organ donation.
It's a data donation, really. Imagine an acceptor cell in the background mesh. It's sitting right next to the boundary where the Overset mesh begins. To solve its equations, it needs to know the pressure value of its neighbor.
Right.
But it has no neighbor on one side. Or rather, its neighbor is an inactive ghost.
So it can't ask its neighbor, hey, ghost, what's the pressure? No answer.
Right. So it looks up, so to speak. It looks into the overlapping mesh, the Overset region, and it finds active cells there. Those active cells in the other mesh are called donor cells.
So the acceptor is basically saying, hey, I'm at coordinate XYZ. Is there anyone in the other mesh who covers this spot and has some data for me?
Precisely. And the donor cells in the other mesh reply, yes, we are active, and based on our position and our values, the pressure here is X.
But wait, the cells rarely line up perfectly, right? The center of the acceptor isn't going to be sitting exactly on top of the center of a donor.
Almost never. And that's the key. That's why it involves interpolation. The source details a few ways this interpolation, this donor search can happen.
Yeah, let's touch on those. I saw distance-weighted, linear, and least squares. Why do we need three different options?
They offer a trade-off between speed, robustness, and accuracy. The simplest is distance-weighted interpolation.
Okay.
The algorithm finds the closest donor cells to the acceptor center. If one donor is really, really close, it gets a higher weight or influence in the calculation. Contributes most to the answer. It's essentially an inverse distance calculation.
Simple enough, fast, I'm guessing. But is it the best?
It's okay for static things, but it can be a bit diffusive. The source seems to strongly prefer linear interpolation for moving meshes.
Why is linear better for motion? What's the difference?
Linear interpolation uses what are called shape functions. In 2D, it finds three donor cells that form a triangle around the acceptor's center point.
Okay.
In 3D, it finds four cells that form a tetrahedron. It then calculates the value based on where the acceptor sits inside that geometric shape. The reason it's so much better for motion is that it's continuous. As an acceptor moves through the donor grid, it transitions smoothly from one tetrahedron to the next.
So you don't get sudden jumps in the data.
Exactly. It's more accurate because it preserves the gradients better. It prevents jumps or spikes in the data as the mesh moves. It is more expensive, meaning it takes more computing power to figure out those tetrahedrons. But for something like aerodynamics, where smooth flow is everything, it's absolutely worth it.
Accuracy usually costs money, or time in this case. But there is a third option mentioned, least squares interpolation. This is fascinating because it's linked to something called implicit coupling.
Implicit coupling. That is the heavy hitter term here. To understand this, you have to realize how simpler older codes might work. Usually it's explicit. You solve mesh A, stop, pass the boundary data to mesh B, solve mesh B, stop, pass the data back. It's like a game of tennis.
I talk, then you talk. A very polite but slow conversation.
Exactly. But with implicit coupling using least squares, the solver treats the whole thing, the background mesh and the overset mesh, as one single giant system of equations.
Oh.
It builds the interpolation relationship directly into the coefficient matrix of the algebraic equation system.
So the data isn't just being passed back and forth between turns, it's being solved all together at the same time.
Yes, the solver is calculating the pressure in the background and the pressure in the overset region simultaneously. From the solver's point of view, it doesn't really know they are separate meshes. It just sees one big interconnected problem.
That must be why the source claims the convergence rate is so good that it's similar to a single mesh.
Exactly that. We'll get to convergence later, but that tight implicit coupling is why modern overset is so powerful and robust. It doesn't feel like two separate simulations stitched together. Ideally, it behaves like one continuous block of physics.
Okay, that makes sense. So we know how they talk to each other. But I want to go back to the ghost cells, the inactive ones. How does the simulation know which cells to turn off? We touched on it, but the source calls this hole cutting.
Hole cutting is the process of creating that virtual void. It's a cell marking procedure, not a cell deleting one.
And it's not static, right? Because the car is moving, so the hole has to move with it.
Correct. For an unsteady or time-dependent simulation, this hole cutting happens every single time step. Imagine a piston moving up in a cylinder at 6,000 RPM. That hole is being recut hundreds of times a second.
Oh, okay, that's fast.
As the piston head moves up, the background cells that are above it, which used to be active air, are suddenly swallowed by the metal of the piston. They must be instantly switched to inactive.
And the ones underneath?
Meanwhile, the cells below the piston, which used to be inside the metal, are now exposed to the air. They have to wake up and become active.
That's the dynamic behavior the source talks about. It's a constant flux of status. But how does the computer decide? The source mentions a layered approach and an alternate approach. What's the difference?
The layered approach is the default, and it's generally the most efficient. Think of it as building a watertight container or a buffer zone around the object.
Okay. Walk us through it. How does it build that buffer?
It starts at the boundary of the overset region, the edge of that patch. Step 1, it marks a layer of acceptor cells there. Step 2, Moving inward from them, it marks a layer of potential donor cells.
Okay, so it's working from the outside in on the overset mesh.
Right. Step 3, it jumps over to the background mesh and finds cells that are near those donors, and it marks them as background acceptors.
So it builds this perimeter fence, this shell.
Exactly. It creates a shell of active acceptor cells.
Yeah.
That is, by default, about 4 to 5 layers thick. Then it simply says, everything inside this shell, deactivated. You're all ghosts.
That seems really efficient because you only have to look at the cells near the boundaries. You don't have to check every single cell in the whole domain. It just assumes if a cell is inside the fence, it's a ghost.
Right. Which is why it's the default method. It's fast.
Yeah.
But it can fail. What if the geometry is really weird and complex? What if the fence accidentally crosses over itself or doesn't close properly? That's where the alternate approach comes in.
The centroid check.
Yes. This is the brute force method. For every single cell in the background region, the algorithm asks a simple geometric question. Is the center of this cell physically located inside the volume of the overset object?
Yes or no?
Yes or no? If the answer is yes, turn it off.
That sounds much more robust. It doesn't rely on neighbor connections or building a fence. It relies on pure coordinates.
It is much more robust, especially for what the source calls close gaps, or very complex shapes. But it's computationally heavier because running millions of those geometric containment checks is slow.
So the advice is?
The source advises using the default layered approach first, and only switching to the alternate method if you get overset intersector errors, which is the code's way of telling you that the fence building failed.
That's a good practical tip. And speaking of closed gaps, that brings us perfectly to section 4. The source spends a lot of time warning us about what happens when things get too close.
The close proximity problem. This is a classic issue in things like gear pumps, screw pumps, or some types of valves.
Right, where you have two metal parts that are either grinding against each other or spinning with just a hair's breadth of fluid between them.
The risk here is literally running out of cells. Remember, we need that handshake. We need acceptors and donors. If the gap between two objects becomes smaller than, say, 1 or 2 cell widths, you might squeeze out all the active cells. The acceptor looks around for a donor and finds nothing, or just a wall, or another acceptor.
And an acceptor cannot donate to another acceptor. It's like two people asking each other for directions. Neither one knows the way.
Exactly. If that happens, the interpolation fails. Or, even worse, you can get island cells.
Island cells.
These are isolated active cells that get trapped between two walls with no connection to the rest of the fluid. Numerically, they go absolutely crazy. They can calculate infinite pressures or velocities because they have nowhere to vent. They just blow up the solution.
So how does STAR-CCM Plus handle this? The source introduces something called the zero-gap interface.
Zero-gap is a specialized tool for this exact problem. When you enable it, the software actively detects when the boundary of the overset region effectively touches or comes within a tiny tolerance of the background boundary or another wall.
And what does it do? Does it try to refine the mesh in that tiny gap?
No, it does the opposite. It closes the gap and enforces a seal. It effectively generates temporary walls between the regions to prevent any flow from trying to squeeze through.
So it basically says, okay, this gap is now too small to resolve accurately, so we're officially calling it shut. No fluid moves here.
And, very importantly, it cleans up the mess. It goes in and deactivates those potential isolated island cells that might get trapped between a zero-gap boundary and a wall. It turns them off so they don't crash the solver.
But there was a big warning label on this feature in the source, a big use with caution sign.
Yes. The source says, and I'm paraphrasing, zero-gap can be less robust. The advice is clear. Only use it if the flow is obligatorily blocked.
Obligatorily blocked. I love that phrasing. It's so specific.
It means, is this a valve that is supposed to seal tight? Then yes, use zero gap. But if it's just two cars passing very near each other and you accidentally trigger zero gap, you might create a magic, invisible wall between the cars that blocks the air that would be physically wrong and ruin your results.
So it's a tool for engineering contact, not for accidental proximity.
Precisely. Use it with intent.
Okay, let's zoom out a bit. We've talked a lot about the math and the mechanics, but why does an engineer actually use this? Aside from the cool factor, what's the big win? Section 5, practical applications.
Well, there's the lazy engineer argument, which, as you said earlier, is really the efficient engineer argument.
The source talks about parametric studies. This one really resonated with me. Let's say I'm designing a Formula One car, and I want to see how the aerodynamics change when I adjust the angle of the front wing. 1 degree, 2 degrees, 3 degrees, up to 10 different angles.
Okay, think about the workflow for that. In the old days, or with a single continuous mesh. You would have to go back to your CAD model, rotate the wing geometry, remesh the entire car and the air around it, and run the simulation.
Then you do it again, rotate it again, remesh the entire car, run the simulation 10 times.
That's days, maybe weeks of work. And you introduce mesh error because every single mesh you generate is slightly different. You're not just comparing the angle, you're also comparing different meshes.
Not a clean comparison.
Not at all. With Overset, you mesh the car once, you mesh the wind tunnel once. To test a new angle, you just tell the solver, rotate the Overset grid containing the wing by 2 degrees.
You don't remesh anything.
Nothing. You just move the grid coordinates, the hole cutting algorithm runs automatically at the start, finds the new hole, establishes the new donors and acceptors, and you are ready to run. You can script this to run hundreds of variations overnight, completely automatically.
That is a massive, massive time saver. It changes the entire design cycle.
It does. The source mentions orienting identical bodies at different relative positions. Imagine testing a fleet of drones flying in formation. You mesh one drone, then you just copy-paste that Overset mesh 10 times and arrange them however you want in the background. It's incredibly powerful.
Incredible. And the source lists some specific applications beyond just cars. We mentioned the lifeboat drop earlier.
That's a classic large motion example. Dropping a boat from a height into water involves what we call 6 degrees of freedom motion. The boat pitches, rolls, yaws, and plunges all at once. The mesh has to travel a long vertical distance. Overset is perfect for that because the boat carries its own high-quality mesh with it as it falls.
It also mentioned window wipers. That seemed like an interesting one.
Ah, yes. Fluid film modeling. This is interesting because it often involves a very thin layer of water on a windshield. The wiper is an Overset mesh moving back and forth. The source confirms you can model a fluid film shell region passing from the background, which is the windshield, to the Overset region, the wiper.
That implies the physics is continuous even for these specialized models.
For many of them, yes. But that brings us to the rules, because you can't just do anything. Section 6, Implementation and Limitations. There are some hard and fast rules you have to follow.
The one physics rule.
This is absolutely critical. All regions involved in the Overset mesh, the background, the Overset, any other Overset regions must belong to the same physics continuum.
So I can't have the background be defined as air ideal gas and the Overset region be defined as water liquid.
Not as separate physics definitions, no. You would have to define a single multi-phase physics continuum that includes both air and water, and then apply that same continuum to both grids. They have to share the exact same mathematical framework.
That makes sense. The matrices have to align for that implicit solver to work. The handshake fails if one side is asking for a variable the other side doesn't even have.
Precisely. If the background is solving for temperature and the Overset is not, the handshake fails.
But there are some models that are just straight up not invited to the party. I have a list here from the source. It says, the feature is not supported for. And then it lists things like defogging.
Right. Harmonic balance, grid sequencing, batteries.
Batteries!
The specific electrochemical battery models in STAR-CCM plus InFOBs, they have their own specialized solvers. And also the finite element method, or FEM, solver. Overset is a finite volume method. If you try to mix it with the structural FEM solver, it won't work in the way you might expect.
So the lesson is check the documentation.
Always check the documentation for your specific version, but generally, if it's a very specialized physics model, you need to verify if it works with Overset before you spend a week setting it up.
And then there's the golden rule of meshing. If you take nothing else away from this deep dive, listeners, please take this. Mesh matching.
This is the #1 cause of error and inaccuracy in Overset simulations. The source is very, very specific about this. Cell sizes should be similar in the overlapping zone.
So if my background mesh has cells that are, say, 10 centimeters wide, and my Overset mesh has cells that are 1 millimeter wide.
You are going to have a very bad time. Think about the interpolation we discussed. If a tiny 1 millimeter acceptor cell is looking for a donor, and the only donor it can find is a giant cell 100 times its size, the data it gets will be completely washed out. It receives one giant average value.
It's like trying to get a high-definition image from a single pixel of a low-resolution screen.
That's a perfect analogy. Or conversely, if a giant acceptor looks for donors and finds 1,000 tiny cells, the algorithm has to work very hard to average them all. It's computationally wasteful and can introduce numerical noise.
So ideally, the cell size ratio should be close to 1 to 1 in the overlap region.
Yes. And the source advises ensuring you have at least 4 to 5 cell layers of overlap where this size matches. That gives the interpolation scheme enough good data to work with.
But that sounds hard. If I have a background mesh that's generally coarse to save cells and I throw a detailed car mesh into it, do I have to manually refine the background everywhere the car might go? That could be the whole domain.
You could, but that defeats the purpose of being lazy.
Yeah.
Efficient. This is where adaptive mesh refinement, AMR, comes back in to save the day.
Ah, so we can use AMR. It's a helper tool.
Yes. Specifically, there's a feature called overset mesh refinement. You can set up the simulation so that the background mesh automatically refines itself to match the size of the overset mesh, but only in the region where they overlap.
That is slick. So as the car drives down the virtual road, a little box of fine mesh on the road forms around the car, travels with it, and then the road coarsens up again after the car passes.
Exactly. The source explains that AMR uses the overset mesh cell size as the target size. It creates that necessary buffer zone of similar sized cells dynamically on the fly. It ensures the handshake is always happening between equals.
Okay, that makes this whole thing much more usable in practice. Now, let's talk about confidence, Section 7, convergence and validation. Because I can imagine a skeptic, maybe an old-school CFD analyst, saying, "You're cutting holes in the math. You're stitching grids together. Surely this is unstable or slow to converge."
You would think so. It's a very reasonable question.
Mm.
But the source addresses this directly. It asks, does cutting the mesh affect the convergence rate?
And the answer.
The answer is, and I quote, the rate of convergence is similar to that of a single mesh of the same resolution.
That is genuinely surprising. I would expect all that interpolation and hole cutting to slow things down or introduce instabilities.
It goes back to that tight coupling and implicit solving we talked about. Because it's solved as one big matrix, the solver doesn't really know the meshes are disconnected. It just sees equations that need to be solved. It doesn't treat the overset boundary as a wall or a break. It treats it as just another connection, albeit a slightly more complex mathematical one.
But as an analyst, I can't just trust the convergence plot. I need to see that it's working correctly. The source gives us a great checklist for validation.
The first thing is always visual checks. And this is a pro tip for anyone starting out. You have different representations or viewers in the software.
Right. I saw overset mesh representation versus volume mesh representation. What's the difference?
The overset mesh representation shows you everything. All of it. You see the background grid, you see the overset grid, you see the overlap region, and you see all the inactive ghost cells. It looks like a complete mess.
Okay.
It's useful for debugging the whole cutting process itself, but it's terrible for looking at the physics.
But if I want to see the actual airflow, the velocity contours.
Then you switch to the volume mesh representation. This one is smart. It hides all the inactive junk. It shows you the physical reality, only the active cells and the valid acceptors where physics is being solved. If you see unexpected gaps, white space, or weird holes in this view, you have a problem. It means your hole cutting failed somewhere.
That's a great tip. The source also mentions some specific field functions, basically variables you can plot. Chimera grid test data.
A terrible name,
Mm-hmm.
but an incredibly useful variable. It shows the interpolation error at the acceptor cells. Ideally, you want this to be 0 everywhere. The source says 0 indicates perfect interpolation. If you see high values here, it means your mesh sizes probably don't match well enough or your donors are too far away.
And overset cell status.
That's your diagnostic flag. It colors the cells by their role. Active is 0, inactive is 1, acceptor is Manico 2. If you plot this on a plane cutting through your object, you should see a nice clean border of Manico 2s, the acceptors, outlining your object. If that border is jagged or broken, you should go back and check your mesh quality.
One last validation point, and it's a big one, mass conservation.
Absolutely crucial. The source advises checking a report called Overset Mass Conservation. Because of the interpolation, it is possible to gain or lose a tiny amount of mass across the interface. The solver has settings to enforce this, but you should always monitor it.
And it mentioned volume, too.
Yes, checking the overset grid volume versus the standard volume. This is to make sure you aren't double counting the overlapping cells in your analysis.
Right, because if you just sum up the volume of all the cells in both grids, you'd count the overlap region twice.
Exactly. The overset grid volume function is smart enough to know to ignore the inactive ghost, giving you the true physical volume of your simulation.
Okay, we have covered a lot of ground. From the chewing gum nightmare of stretching meshes to the elegant handshake of donors and acceptors.
It really is a remarkable technology when you step back and look at it. It turned problems that were basically impossible 20 years ago, like a helicopter rotor spinning while the entire helicopter moves forward, into standard, almost everyday simulations.
Let's summarize the journey for the listener. We started with the core concept. Two grids are better than one, especially for large motions.
Hmm.
We met the cast of characters, active workers, inactive ghosts, and the acceptor border guards.
We learned the secret handshake, linear interpolation from donor cells using geometric shape functions.
We saw the violence of hole cutting, deactivating cells to create a virtual void, and the choice between the layered, which is fast, and the alternate, which is robust, methods.
And we learned the golden rule: match your mesh sizes in the overlap region or face the consequences of bad interpolation.
And we learned that for complex motion gearboxes, lifeboats, overtaking cars, overset is often the only viable path forward.
It really is.
I want to leave the listener with a final thought. We talked about that dynamic overset behavior mentioned in the source, things like pistons changing from walls to overset boundaries automatically.
It's seamless. The mesh adapts to the physics, not the other way around.
It makes me wonder about the future. If the software is already this good at ignoring parts of the mesh, cutting holes in itself, and stitching things together on the fly, are we slowly moving toward a world where we don't mesh at all?
That is the big question, isn't it? Meshless CFD methods exist, and they effectively treat the whole domain as a cloud of points that act like donors and acceptors for each other. Overset is, in a way, the bridge between the rigid, structured grids of the past and the fluid, adaptive future of simulation.
A bridge built on virtual holes? I love it. Thanks for listening to this deep dive into overset meshes. We'll see you in the next simulation.
Keep meshing.